So I give you this vector field F equal to yi. Now let's draw the vector field of this on the graph. So you can see that the vector field here is going to point in x direction only, and it's going to increase with the value of y. So let's take a look here. So if I pick y equal to 1, maybe this point, x equal to 1, y equal to 1, I'm going to get I'm going to do this f1 1, that is going to be equal to I, right? So something like this. But if I pick 3 1, well, 3 doesn't matter here because the component for the I depends on y. So this also comes out to be just vector I. So at this point, 3i comes out to be this. And same for any other point. So in terms of vector field, it's going to look like this, as long as y equal to 1. But if y equal to -1, it's going to go in this direction. Alright, this direction. Alright, you get the point. Alright, what about I move to y equal to 3? And if I move to y equal to 3, you can see that the component for I will be increased instantly. 3, right? Instead of having a vector of size 1, at this point y equal to 3, it's going to be 3 times as long. This 3 times as long. Same here, 3 times as long. If I go to 5, it's going to be 5 times as long. So you see the dynamics here. Some of them is going to go slower, some of them goes really fast. As you go up in y direction, it's going to be faster. Now, let me pick a point. Maybe right here. Just any point. I'm going to pick maybe 3. That is the point I'm interested in. The point I want to know the behavior, the characteristic. So at this point, it's going to have neighborhood. Okay, so let's magnify this point. So I'm going to pick this point. Let's say that the point that I pick is 3 2, and I magnify this point right here. This point has the neighborhood. So imagine the flow regarding the vector field. On the left hand side, you have small arrow going in, and on the right hand side, you have the small arrow goes out. Up here, you have a bigger arrow goes in, and the same amount of the same size of arrows goes out. Why? Because the size of the arrow depends on y value. As you can see here, y is the same here, same length. And up here, you are going to see a bigger, longer arrows go in and longer arrows go out. Okay, now you can see on the left hand side this is goes in, and on the right hand side this is goes out. I told you about divergence. Oh, let's start with the divergence for this one, by the way. Okay, divergence, if more flow goes in, it's going to be negative. If more flow goes out, it's going to be positive. But you can see that if in this case we have this arrow goes in, and in the end it goes out, same arrow. This on the next one goes in, and we have the same arrows same size, go out. Small one goes in, small one goes out. So at this point, can you predict what the divergence of this point is going to be? As you can see here, same amount of flow goes in and the same amount goes out. So which means that we are going to predict divergence of f to be 0. Why? Because amount of goes in and amount of that goes out are equal. Equal. So let's check by using the formula. So formula, we want to find divergence of f xy, and we know this is equal to del dot f. So let's find that. Del dot f, by the way, del equal to partial diff of something with respect to x plus partial diff of something with respect to y, j, and partial diff of something with respect to z, k. Now let's find the dot product. Okay, so start with the first component, I, and I have this component right here. So I have this dy by dx I plus next component, but then it turns out that the components for the vector field doesn't have j, so this is equal to partial diff of 0 with respect to y, j. And for the next component, you can see that f right here doesn't have k component, so that means it has 0 for the k component. So we have this partial diff of 0 with respect to z, k. And you can see here, this comes out to be 0, 0, 0, which means that the divergence for this vector field, any point comes out to be 0. Alright, just like we predicted. So here, no expansion and no contraction. All right. Okay. So this is the result for the first example in terms of divergence. Let's take a look at the curl of this example. Same example. Okay. By the way, I'm going to magnify to use this again. This picture. All right. I'm going to move this down here again. So what we have right here is a point that we are interested in, and we have the surrounding, something like that. It has been magnified, so it's really big here. And as you can see from before, the vector at the lower part is going to be smaller than the one at the upper part. So we have smaller one here out, bigger one here, and bigger one out, and bigger one here, and bigger one out. Imagine these arrows to be force. Do you see like something spinning in this neighborhood? This is like you apply bigger force up here, right? And you apply less force down here. If you imagine this, more force at the upper part, it's going to spin this disk in this direction. Right? Because of this. Because of more flow up here. It doesn't matter with with the other side of the flow. As you can see here, more force in the upper part, and that is going to cause the disk to circulate in this direction, and it's clockwise direction. So if I predict and if we calculate the curl, the sign of the curl should come out to be positive or negative clockwise. Okay, it's going to come out to be negative. Okay, so let's check whether it's going to be true. So what do we have here? We have f, and we want to find the curl to prove our prediction. So we have this f, and we want to find curl. Curl of f is going to be equal to this. I'm going to bring down the formula here because it's easier to use. So it's going to be equal to this. Alright, so let me write that formula down here. So this is equal to p with respect to y minus n with respect to z I plus m with respect to z minus p with respect to x j plus n with respect to x minus m with respect to y. Okay, let's do some calculation on this. So here we have, this is m. What we have here is m, and n is equal to 0 and p is equal to 0. Alright, so p with respect to y, and we can see that p is equal to 0, so comes out to be 0. Now minus n with respect to z, n is equal to 0, so we don't need to do anything here, comes out to be 0 for sure, plus m with respect to z. Now we take a look at m right here. M with respect to z comes out to be 0. Now p with respect to x, but p here is 0, so 0. Seems like nothing is happening right now, so let's take a look at the last term. So we have j right here. Now the last term, n with respect to x, n right here, 0, so comes out to be 0, minus m with respect to y. So m right here equal to y, so diff y with respect to y. Last component. So in the end we have this. This is equal to 1, so minus k. Alright, so we can see minus sign, this is clockwise circulation. Imagine bigger force here, bigger force here, smaller force here, smaller force here. Of course the forces on the top is going to win over the ones at the bottom, and we are going to see this kind of circulation around this point P. Okay, so this is very easy example, but it shows how divergence can be calculated and how it tells us about the amount of flow goes in like that, and the amount of flow goes out. Oh, I didn't know that I wrote it wrong. This is go out, goes out. Alright, same amount, so it comes out to be 0. Alright, and then this example also shows us about the how the flow, the size of the flow here, the difference in size causes the circulation around this neighborhood. Right, clockwise circulation in the neighborhood of point P. Alright, Now let's move to a more complicated, a more challenging problem that are related to divergence and curl. So we have this new vector field and it looks more complicated. So we have M right here, M, N, and P. M depends on X, Y, Z, N, X, Y, Z the same, and P right here. And the first one, for this one example, we are going to find the divergence. So let's find out about that. So divergence, at this point we know the formula to use. This is divergence of F is going to be equal to del dot the vector field F. So here it's going to be equal to the partial diff of the first component, M with respect to X, plus partial diff of N with respect to Y, plus partial diff of P with respect to Z. Okay, let's find out about this. So this is going to be equal to partial diff of M, that's X squared plus 3Y, with respect to X, plus partial diff of N, which is Y cubed plus 2YZ with respect to Y, plus partial diff of P, which is ZX minus Y sine Z with respect to Z. Well, this is not hard at all, so you know this is equal to 2x. This is equal to 3y squared plus 2z plus x right here and minus sine z. In the end, you can answer with confidence that this is equal to 3x plus 3y squared plus 2z minus sine z. Okay, so that is the divergence of f at any point x, y, z. That's why you have this variable x, y, z in the answer. Alright, so what about, I want to know the contraction and expansion behavior at the origin. What about, I want to know what happens at 0, 0. So let's find out the expansion contraction. So 0 goes in, so I want to find this divergence of f at 0, 0. 0 goes in, this all become 0, 0, 0, 0, 0. So it comes out to be 0. This is telling me that if I go to this, the origin, no expansion, no contraction. Alright, so this is something that you can interpret out of the value that you get from the calculation. Alright, so next thing, let's try to find the curl of the same vector field. Same thing as up here. Alright, and then we are going to find out the behavior regarding the circulation around the origin. So let's start with the finding the curl. The curl f is going to be equal to del cross f, and I'm going to use the formula that I gave to you before, the shorter one. So this is equal to py minus nz I. Once again, this is cross product. It has to come out to be vector. Alright, so next, m with respect to z minus p with respect to x, j. Last component, n with respect to x minus m with respect to y, k. Okay, now we have MNP up here. MNP. Let's do this quickly. I'm going to differentiate P with respect to Y. So let's take a look here. P with respect to Y. So I see Y right here. The result of P with respect to Y is minus sine Z. Okay, there is a typo. Alright. Okay, let's get rid of this Y. It's going to complicate the example that we have here. Let's assume that we don't have Y right here. So the first thing I'm going to do is to differentiate P with respect to Y. P with respect to Y, and you can see that P right here doesn't have Y in them. So it's going to come out to be 0. Now, I differentiate N with respect to Z. And I look at N, I see Z right here. So if I differentiate this with respect to Z, I get what? 2Y. And that is the first component. Plus M right here with respect to Z, I don't see Z in there. So this is going to come out to be 0. Now, diff P with respect to X, I see X, 1X right here. So I diff this, I get Z. And that is the second component. Now the last one. I diff N with respect to X, and you take a look here. N right here doesn't have X in it, so it has to come out to be 0. Now I'm going to differentiate M with respect to Y. This with respect to Y comes out to be just 3. That is the last component. So when you combine everything together, you get minus 2y I minus zj minus 3k. Alright, and that is the curl at f, curl of f at any point x, y, z. If you want to study the behavior of the circulation at any point of this vector field, you just put in x, y, z. For example, I want to know the circulation at the origin. So let's find the curl at the origin. The curl here at 0. It's going to be equal to 0i minus 0j minus 3k. So here this is equal to minus 3k. And as you can see, the sign right here, negative, means that the circulation is going to spin in clockwise direction. Clockwise circulation. Okay, so same vector field. The first thing, the divergence tells us about contraction, and the curl tells us about the circulation. Right, two things, two behaviors that we can get out of these two calculations. Okay, this is about expansion, contraction. Now, let's try something more about this vector field. This is line integral. We have done this in the last lecture. Let's try again. In the last lecture, we have an example about finding the work done along the path. So that is line integral. Let's do something like that over here. Okay, so we have this vector field same as the previous one, but in this case we are going to find the line integral along this vector field. And then it's given to us that find find line integral along a line connecting this line connecting point 0, 0, 0, the origin, and the point 1, 2, 0. So what do we have here? We have this vector field and we have this line in 3D. I told you before that line in 3D can be represented in terms of parametric function. It can be represented in terms of this r of t, but they don't give you directly here. They give you something else. They give you points. The first starting point and the end point. In order to continue with this, if you remember the formula that we used to calculate the work, so the work done is equal to the integration along the curve of vector field dot dr. That's what we had in the last lecture, and we also learned that in order to use this, it's better to use another form, and that is equal to f in terms of t as a function of t dot dr by dt, and we integrate this with respect to t. This goes together, and which means that when it comes to integration here, this is not about coordinate, it's about time. It's about time. So time starting from a to time equal to b. So in order to find this work or line integral, we need two things. We need the vector field, which we already have from the problem, but what we don't have here is the r. This we don't have it yet. So let's find out what this r of t is going to be. So this r of t is going to be line equation in 3D. At this point, we know that it starts at 0, 0, 0 and ends at 1, 2, 0. And we are going to use this two points to create this r of t. And we learned this at the beginning of the class that in order to construct this, we need two things. We need starting point in order to construct a straight line in 3D. We need a starting point and we need vector in the direction of the path. Right, so this r of t is going to be equal to the starting point. Let's say that r at time equal to 0 plus the vector that we are looking for in the direction that we want to move it to, and times the time. So we have this point starting at point 0, 0, 0 and it ends at point 1, 2, 0. So we want to create this line in 3D and we want to represent this in terms of r of t. In order to do that, let's put this point, first point A and this point B. So the starting point, the starting position for this line is going to be this, which means that this start point, the coordinate of the starting point, I shouldn't say coordinate, that should be the position vector of the starting point. Starting point, right? So this is going to be equal to position vector of the starting point, that is 0, 0, 0. And now we need the vector in this direction that moves from A to B. So vector AB right here is going to be equal to 1 minus 0, 2 minus 0, and 0 minus 0. So we have this vector V. Vector V right here is going to be equal to vector AB, move from A to B. Right, so this is 1, 2, 0, t. So in the end, this is equal to vector of t, 2t, and 0. Or you can represent this in terms of ijk, equal to ti plus 2tj and plus 0k. So this is the equation for the line in 3D that we want. So let's keep this. This is path in 3D, and we are going to perform integration on this path. Alright. We want to perform integration of this f along r of t equal to what we just found, ti plus 2tj. Okay, now let's continue. Now at this point we know that the line integral and we have seen this from calculation of the work calculation, work done. We did this in the last lecture. It's going to be equal to the integration of f, and we are going to use the form that is easier to do calculation, that is f in terms of t dot dr by dt, and integrate this with respect to time, starting from time equal to a to time equal to b. Okay, let's find out about all these terms. Okay, let's start with the easiest one. Now we need this. Differentiate dr with respect to t. We already have r right here, so we know right away dr by dt is equal to I plus 2j. Right? Now the next thing we need is this vector field in terms of time. Alright? Looks simple, but if you look at this, we have the vector field in terms of x, y, and z. We can't use that right away, so we have to find a way to translate this into the vector field that depends on time. How to do that? Let's take a look here. This is the line equation for the path in 3D. Path in 3D. And you can see that when it comes to this sort of equation, the first component right here, that is x component. It tells us about the location in space. So this y component, and if we have the component for k, that is going to be z component. Oh, coordinate. I am sorry. X coordinate. and this is y coordinate. Well, let's do a summary right here. So x coordinate is going to be equal to the component of I in RT, which is equal to t. Y coordinate along the path is going to be the coefficient in front of the j component, that is 2t. Now z coordinate is going to be equal to 0 because here we don't have that. So this is going to be equal to 0. Now we can use this information to translate f in terms of x, y, z to make it depends on t. So f that depends on t is going to be equal to, let's take a look at this first term, x squared. But now we know that x equal to t, so this is going to be equal to t squared. Next term, 3y. Now we know that y equal to 2t, so this becomes plus 6t I. Next one, y cubed, but we know that y is equal to 2t, so y cubed becomes 8t cubed plus 2yz right here, but we know that z equal to 0, so this thing is going to go to 0, so I have 0 right here. J plus, let's take a look at the last component, zx here. So z, we know that is equal to 0. This is going to be equal to 0. Minus y sine z. We know that z equal to 0. Sine z, sine 0 become 0. So we have minus 0 right here. And that is k. Now let's put everything together. Right, I need more space. So this is minus 0 plus 0 k, which means that ft right here is going to be equal to t squared plus 6t I plus 8t cubed j, and that's it. And we have f in terms of t. And now what we need to do next is to find the dot product. But before that, let's find what a value here and b value here. So we start from 0, 0, 0, and then we end at 1, 2, 0. So we know that at point A, this is time equal to 0. Now let's find out the value of t that we can put in here that gives us this point 1, 2, 0. And you can see that if you want 1, 2, 0 at the end, you need to put t equal to 1, right? And it comes out to be 1, 2, 0. So at this point, time is going to be equal to 1 second. Now we use this information to perform the integration, which means that start at time equal to 1 and ends at time, start at time equal to 0 and ends at time equal to 1. Okay. Line integral equal to integration of f dot dr. So let's take a look here. F is this, and dr by dt is this. So dot product, I'm going to take the first component of f and dr by dt dot together. So this I have t squared plus 6t. Alright, and that times with 1 right here, so nothing changes. Now plus the product of the next component, which is j component, 8t cube, and we have 2 right here. Product of that becomes 16t cube. And that's it. And we need to integrate this with respect to time, starting from time equal to 0 and time to time equal to 1. And this is equal to t cube plus t square, 3t square plus 16t to the 4th divided by 4. Oh, by the way, we have this divided by 3 right here. So we have to evaluate this at 0 and 1. So cancel this. We have 4. So 1 goes in, we have 1 over 3. 1 goes in, we have 3. 1 goes in here, we have 4. And 0, everything goes to 0, so minus 0. So in the end, here we have this line integral of this vector field along this path equal to 7, 1 over 3. That is the answer right here. So the only formula that you need is this. Alright, and the most important step is to construct this line equation. You have to be able to construct this. Sometimes it's given to you directly, and in this case it's given to you as a point, and then you have to use those vectors that you learned at the beginning of the semester in order to find this out. But in the end, you need RT and you need F in terms of T in order to carry out the calculation. Alright, so that is the line integral of this vector field over the path that we are interested in. Okay, last example of today. So this one, we are going to talk about the conservativeness of the vector field, which is something that we already did that in the last lecture, but it's going to be related to something we learned today, so let's take a look how. Alright, so I give you this vector field in 3D, and I ask you the same question as last time. Is this vector field conservative? And by now you know that if a vector field is conservative, it means that this vector field can be derived from a gradient of a certain function. So if you can prove that this f can be derived from this, then your vector field is conservative. So in order to find out about this, last time we have this method. So we have this, right? And have these components of vector field, and we know that this, if it's conservative, this is going to be equal to df by dx, df by dy here, and this has to be equal to df by dz. We want to find out, is it possible to find such f that make this happen? Let's find out. I am going to integrate. So the first thing we need to do is to find the first version of fxyz. It's going to be integrate of the first term 2xy in terms of x with respect to x, and let's find out. Okay, this is equal to x squared y, but this is indefinite integral, so which means that you can get constant out of that first one, and this constant can have the variable that you didn't perform the integration on, so it can have y and z in there. Y and z, right? Because here you diff with respect to x, you treat y and z as constant, so it can go away during the partial differentiation, so it can can get lost along the way, so which means that it can show up in the constant right here. Now, function f(x,y,z) must be able to be the same as the integration of the next component, x squared plus 2yz, but this time with respect to y, dy. Here we have this, integrate this with respect to y, we get x squared y plus y squared z, and now with some constant, but this constant, it can have x and z in it, because when you perform the partial diff with respect to y, you treat x and z as constant, so it might show up right here. Now, last one of the xyz can come from the integration of the last component, that is y squared. This time you have to integrate with respect to z. With respect to z. Now, with this, easy. You get y squared z plus another constant that can have the variable that is not z, which is x and y. Alright, so we have these cases, and we have to find out whether it's possible to make them equal to each other. Can we make this equal to one another? So let's find out about that. Alright, let's take a look at the common terms. So first one, x squared y. This one has that. Next one has that. But the last one, we have 3. Let's take 1, 2, and 3. Number 3 doesn't have that. So the only location that it can have this x squared y is in the constant. So let's take a look here. Constant is allowed to have x and y. So yes, it's okay to put x squared y right here, and it's a common terms with the number 1 and number 2. Now let's take a look at the next terms in number 2, which is this y squared z. Y squared z doesn't have is not in number 1 in the first place, so let's take a look. The only location that it can appear is in the constant. So if you look at the constant, you can see that constant is allowed to have y and z, so that's good. We can put y square z right here. Now it has the common terms with number 1, and you can see number 3 right here has this common term. Okay, common terms, x squared y, x squared y, x squared y. Common terms, y squared z, and y squared z. Now we have this. What to do with this? It means that we don't need it, because right now 1, 2, 3 is already equal to each other. So we can set this to 0. So it means that here 1 equal to 2 equal to 3, which means that we can find f such that vector field equal to the gradient of this f, which means this vector field is conservative. Alright, so this is old stuff, but it's going to be related to what we learned today, which is curl. So that is the answer. We already got the answer. Let's compare this with the curl method. The curl method, it says that this is theorem. It has been proven. Theorem, it says that if curl f is equal to 0 at all point, at any point x, y, z, then f is conservative. That's it. all you need to do is to compute the curl. And you can know right away, you can determine right away whether this vector field conservative or not. So this is the theorem that we are going to use. The curl is equal to 0, then conservative. So let's find that. Curl of f equal to the same formula, py minus nz I plus mz minus px j plus nx minus my k. Alright, we have m right here, n right here, and p right here. So let's find out. I want to differentiate p with respect to y. So I get 2y out of that. I differentiate n with respect to z. I get 2y out of that. Right here, just 2y minus 2y plus m with respect to z. We don't see z in there, so it comes out to be 0. P with respect to x, no x in there, equal to 0 here. Plus n with respect to x, I see x squared right here, so it comes out to be 2x. And m with respect to y. Diff this with respect to y, I get 2x, so minus 2x, k. This goes to 0, goes to 0, goes to 0, which means that the curl for this one is equal to 0. And you can answer right away that this vector field f is conservative. And this is one use of the curl. Besides finding the behavior about the circulation, you can use curl to find out about the conservativeness of a vector field.